Hey, what's going on, everyone? We'll be starting in just one moment. Let's get things on the road. Okay, so we have data science, fun stuff. How's it going, everyone? Hello. And let's go. Let me get the link for you all to sign in for the events. Let's see. Should be a pretty fun talk today. So 3:30 a.m. Wow. It's about 5 p.m. here, Eastern Standard Time. So yeah, today is all about data science. So here's the link for you all. Make sure to come and check in for the events. Post this in our Discord too. Intro to data science. So we have check in. Boop. Yeah. On my school internet right now, it's giving me a little bit of trouble, but thankfully all is good. 3 p.m. MST. All these different time zones. It's big worlds. So, I mean, who has experience in the chat here pursuing data science? Like who and what sort of tools you have experiences with, or do you have experience with? So we'll be covering quite a bit today in terms of talk about Python and like R and different libraries for like Python, for example. It's quite a lot of things to possibly cover. I'm curious what everyone is, where your interests lie, where your experiences lie in that regard. Data mining course in college. We use a tool called Orange. Okay, interesting. I've never delved into data mining overall, like sort of in and of itself. I've done some, like how would you contrast that with overall, I guess, just data science as sort of a larger field? I know Python, and I tried to make a small project on Google Colab once, but failed to load the CSV. Oh, that must be frustrating. But I mean, it sounds like you have some experience at the very least. So I guess that's good. Yeah. So I mean, today we're just going to go through some of the most, I guess, fundamental things, like talk about data science, what it is, what it aims to accomplish, different tools and the like that allow us to achieve just that. So I'm going to get some Google Slides up, and we will get started with that. Kind of learn all about the beauty of data science, at least the introductory beauty of data science. Let's see. It was very similar, basically doing statistical models and fitting data to form inferences before they started calling it data science. Just no machine learning / neural network stuff in that course. Okay. Yeah, seems like a lot of overlap then. So, yeah, I mean, I'd imagine it's just a subset of data science overall. So I'd love to learn more of the Python-based frameworks like TensorFlow, pandas, SciPy, NumPy. Yeah, I actually have quite a few slides on that. So basically give a little bit of a introduction to at least the concepts of it. So K means clustering, etc. Okay. So, well, I think we've got a bit of a good intro. It's interesting hearing your guys' experiences and the like in it as well. So, well, with that, let's just sort of jump in. So we got intro to data science. So yeah, data science is actually not a field that I've specialized in heavily myself. I definitely learned a lot putting together sort of presentation, though, and the like. It's definitely something that interests me and that I've aimed to really get a deeper understanding of. So I don't know. It's certainly interesting, especially to understanding the ways that data science and coding intersect overall. I think it's especially interesting. So, but anyways, so we have intro to data science. Let's just kind of jump in. So some of the things that we're going to talk about overall: intro to data science, open source in data science, tools, community collab, data sets, data engineering, data visualization, machine learning, privacy and security, challenges and considerations, case studies and examples, future trends, Q&A. So with that, let's just sort of dive in. So, oops, hold on. It should be intro to data science, but essentially, data science aims to extract meaningful insights and knowledge from data, both structured and unstructured data. Combines elements of statistics, computer science, domain expertise, and data analysis to uncover valuable information, patterns, trends, and correlations that can inform decision-making and solve complex problems. So the popular data science tools that we'll be going over: Python or Jupyter Notebook. Python, as we sort of talked about and saw in the chats. You can see some of these things pop up, right? Like NumPy, Pandas, scikit-learn is another big one. TensorFlow is a pretty interesting example because I know that deals with, that's for AI and machine learning overall, what I recall. It's very interesting stuff. So we'll come to talk about some of these different technologies throughout the night. Okay, so I guess some approaches to data science as a whole. There's especially these ones that we covered, like NumPy, Pandas, scikit-learn, Matplotlib, and something like R. There's a lot of open source overlap as well that you can kind of dive into, and there's quite a few benefits to stuff like that, honestly. A lot of stuff doing with community and collaboration. So like these sorts of tools have active and diverse communities of developers and users who contribute to the software's improvement, provide documentation, and offer support through forums, mailing lists, and online resources. This sort of community support can be invaluable when troubleshooting issues or seeking help. There's a lot of, let's see, oops. Oh, that's not what I want. But I don't know. I mean, I guess with these, is there anything in particular anyone's particularly interested about in terms of like diving deep? See, is this going to be a high-level overview for beginners? Because I don't know anything. Yes, hopefully just going to cover quite a few different areas, quite a few different aspects of data science. And to like some of these tools that we have in particular, like with Python, we have these libraries that are pretty common for data analysis in particular. So, but I mean, I guess in that case, so the community collaboration aspect. So community collaboration is a fundamental aspect of some of these data science projects. It involves individuals from diverse backgrounds, often from around the world, coming together to contribute their knowledge, skills, and time to develop, maintain, and improve such tools and resources. So this collaborative effort often results in high-quality, well-maintained tools. So the scale of such projects can differ. in terms of this community collaboration aspect, from the smallest one-man weekend projects to enterprise-level applications and tools. Larger open source projects often have a governance structure, like again with these like SciPy and Scikit rather, Pandas, NumPy, Matplotlib sort of tools, which includes like community members and decision-making processes. So they can include voting on project direction, releases, and community policies. So these sorts of communities organize conferences, meetups, and events where members can meet in person or virtually to share knowledge, network, and discuss the latest developments in data science projects. So with that, in terms of like the more coding-focused community and aspects of collaboration, data scientists, software engineers, enthusiasts from the community can contribute code to these sorts of tools that we have here. They may add new features, fix bugs, optimize performance, and maintain the code base. There's also code reviews. So peer review of code is essential for maintaining code quality and correctness. So community members may participate in code reviews, ensuring that contributed code meets the project's standards. There's issue tracking and bug reports. Community members may play a crucial role in identifying and reporting issues or bugs in such software. They may submit detailed bug reports, which can then help developers diagnose and fix problems. So in terms of use, areas of community collaboration that correspond with the use of any sort of software application, collaborators can create and maintain documentation for these data science tools. This includes user guides, tutorials, and API references to help others understand and use the software effectively. There's user support. Active community members provide support through forums, mailing lists, and social media. They answer questions, troubleshoot problems, and assist other users in making the most of such tools. So for translation and localization, in more global projects, community members often volunteer to translate software and documentation into different languages, making the tools more accessible to a global audience. And then there's also aspects like feature requests, where users and developers can suggest new features and improvements for such projects, like the NumPy and the Matplotlib, and especially. So community input helps shape the roadmap of these projects, ensuring they meet the needs of a broader audience. For data science focused aspects of community collaboration, there's collaborative research, where these sorts of projects serve as platforms for collaborative research, just overall, I guess. Researchers from different organizations and backgrounds work on solving complex problems using such tools. Data sharing. Some projects even involve sharing data sets. The community can contribute data sets and share them with others for research and analysis. And then as terms of education and community, so many data science projects run educational programs, workshops, and webinars. Volunteers may organize and lead these initiatives to teach others how to use software effectively. Again, many of these communities organize conferences, meetups, and events where members can meet in person or virtually to share knowledge, network, and discuss the latest developments in data science projects. And MLH's bread and butter, projects can even organize hackathons or, even data science challenges, encouraging community members to collaborate in solving specific problems or improving the software. So that is the best of the best in data science in terms of community collaboration, most often exemplified in open source software. But I don't know, it's a fun spirit to definitely explore and get involved with, especially for new developers. Those sorts of communities, you can learn quite a lot in those more, open and more open source softwares, hence the name. But still, definitely a good thing to do if you are a newer developer. Like, how many people here in the chat, how many of you are newer to data science overall? Like, I know we had some people that have some experience. Well, and for the people that have experience, and for those who don't, have you delved into open source data science? Have you delved into non-open source data science? And how much did community and collaboration play a role into your pursuing of data science in either of those contexts? So more of an open question to everyone as we keep moving through. But I think it opens up points for a pretty interesting discussion. So with that, again, with some of these more like open source driven projects and more community focused ones, there's like areas of cost effectiveness, but nothing too crazy as of what we need. Well, I guess there's some. I guess we can focus on these real world examples of the application of data science in some of these companies. So, for example, we have Airbnb at the bottom. They have their dynamic pricing model, which is it utilizes a framework called Apache Airflow for orchestrating data pipelines. So it essentially allows Airbnb to efficiently process and analyze vast amounts of data related to property listings, user behavior, and market trends. They employ some of those tools, like those Python libraries we saw, scikit-learn, and another one called stats models for building their dynamic pricing model, which adjusts prices based on factors like, again, the demands, seasonality, and local events. So that's how Airbnb has kind of utilized and leveraged data science to the benefit of their operation, of their business, of their projects. There's also Uber. So Uber developed something called Kepler.gl, which is a data visualization tool for geospatial data. It allows users to create interactive and customizable maps, very crucial for Uber in terms of their decision making and just overall operations. So the tool is widely used within Uber for visualizing and analyzing data related to transportation and traffic patterns, ultimately. We have Zillow. Zillow uses all sorts of data science tools themselves. They employ the R programming language, one of the tools that we touched on briefly before, for statistical analysis, as well as Python with, again, these libraries like scikit-learn for machine learning. The data science team even contributes to different data science tools and projects, like making improvements to such tools like XGBoost, which they also use for machine learning. NASA, everyone knows NASA. They have the Planetary Data System, which archives and shares vast amounts of data collected from space missions. They actively use things like Python, Jupyter Notebooks, and libraries like AstroPy and SpacePy, of all things, to analyze and visualize planetary data. They also contribute to the overall scientific Python ecosystem. And then we have, last but not least, Walmart. They use the Apache Spark, which is a big data processing framework for various data analytics tasks. They process and analyze data from sources like customer transactions, supply chain, and social media to gain insights into consumer behavior, inventory management, and marketing strategies. So these sorts of real-world examples demonstrate just how data science is omnipresent, really, and the solutions that they bring give all sorts of benefits to various organizations and communities and groups, or even just the individual, because honestly, what it's all about is addressing complex challenges and at the end of the day, but also helps with reducing costs and, again, for I guess just that in and of itself kind of gets the point across. So these sorts of data science frameworks and tooling are essential components of data science and analytics across different industries, ultimately fostering innovation and cost-effective solutions. So, yeah, it really, truly is everywhere. And two, this is really just data science as applied to these big, great projects with these massive industries and groups and organizations and the like behind them. But if you really think about it, it kind of exists at every scale. You know, you can analyze the averages of anything in life. You can get all sorts of statistical readings and data from all sorts of things in life. It's really just about taking one particular thing, seeing its behavior over time, and just inferring things from there. Very, very interesting when you really think it through. Okay, so in terms of data science solutions overall, customization can certainly help with your data science tooling. As we saw, like quite a few of those companies ended up developing their own customized solutions to things. Like we had Uber, who developed their own solution for geospatial concerns. Even researchers and the like, they'll often require customized data analysis and modeling solutions to fit unique requirements of any sort of projects that they're working on. So that's where things like Python and R come in. They can provide extensive libraries and packages, enabling researchers or anyone else to create tailored workflows. So as we were talking about before, like with scientists, we were talking about NASA and the like. So you have a scientist working on climate modeling. They can customize the algorithms in a scientific computing library like NumPy or SciPy to suit their research needs. So I guess that's kind of like the flexibility for research projects. In terms of learning and skill development, aspiring data scientists and researchers can benefit from customization to gain in-depth knowledge of data science techniques. So by working with these libraries we've been talking about, frameworks like scikit-learn or TensorFlow, individuals can experiment with various algorithm configurations and gain a deep understanding of how machine learning models work. For adapting to specific market conditions, well, I guess we can go over that. It is interesting. It is an aspect of the world. So anyways, startups often operate in niche markets with unique challenges. Customizing data science tools allows them to adapt to these market-specific requirements. So as we talked about, like with, I guess with Uber, like they develop their own custom tooling for geospatial stuff. I don't know, that's just the coolest thing to me. You could have a healthcare startup that can customize natural language processing libraries to develop specialized healthcare information extraction models. Or you can have a startup in the e-commerce sector that might leverage customized recommendation algorithms using certain frameworks built exactly for that. So, and maths, let's see. So is data science really math focused? From what I understand, well, I don't know, because I've looked into this a tiny bit myself. Because it kind of means, I guess the question is like, what sort of data science do you want to get into? Because with programming, for example, there's different types of programming that'll take more math than others. So for basic front-end web development, for example, you really don't need any heavy math to be able to do a viable job. As long as you know basic algebra, like basics of the basics in terms of being able to move a variable around so that you can do proportions or so you can create like proportional relationships and the like. It's basically all that you need for front-end web development. But it's going to be a very, very different story if you're going to be doing, I don't know, just anything intensely math heavy. Like if you want to do scientific computing and figuring out how to optimize algorithms in terms of their speed or anything of that sort, then probably going to have to get some pretty heavy math underneath your belt. For data science, again, I'm not too learned on the field overall. I'm still fairly new to it myself. But I'd imagine the same sort of dichotomy or the same sort of continuum exists overall. I'm sure there's some areas where it's less math heavy. There's others where it's very, very math heavy. I would definitely look up that yourself and see. Definitely, I've heard that having a strong background in math certainly helps, especially things like statistics as a whole. I'll definitely look into. But I don't know. Hope that at least gets you thinking at the very least. So with that, yes, adjusting to specific market requirements, cost-effective solutions as well. So for example, startups can't always afford proprietary solutions that come with high licensing costs. They can use customized, maybe more smaller scale tools. that they can use to scale as the company naturally grows. It can provide a cost-effective way to address their data science needs. For integration with existing systems, again, going back to customization, large enterprises often have legacy systems and infrastructure in place. A more customized solution can be customized to integrate seamlessly with these sorts of systems. I have friends that work at IBM that are and some that work at different financial institutions in terms of programming. And let's just say it is not running on the latest and greatest programming solutions. Being able to, I guess they have a few different ways to go forward. Those friends, they have to learn these very archaic languages, and they don't seem to have the most fun doing it. But it can also just lead to inefficiencies as well. If there's like a new, with all these years that have passed, I'd imagine there's different problem sets that pop up now that the current tooling, or that the older tooling that they currently use, can't really adequately handle. Possibly that's the case. I can't speak for certain, but certainly if there's new data science tools that are just the cream of the crop, being able to interface them with some of those legacy systems would be invaluable. So searching for more customized solutions in that space will definitely be a pretty powerful thing. So for enhancing competitive advantage, customization allows enterprises to address data security and compliance concerns by enhancing competitive advantage. So by tailoring their solutions, companies can gain particular advantages, like we saw with Uber. Again, just amazing example where they made their own geospatial tools. Or two, like a retail giant can customize machine learning models to optimize pricing strategies, inventory management, and demand forecasting, aligning these models precisely with their unique business processes. And then for data security, customization allows enterprises to address data security and compliance concerns by fine-tuning access control, encryption, and other security measures in their in their data science stack. So a financial institution can customize the authentication and authorization processes to meet regulatory requirements, for example. Let's see. Any questions right now from anyone? Because I know there's quite a bit kind of walked through. Well, just on customization too, we have quite a few other areas that we can cover too. I know there's a bit of interest for covering different tools like Python and R and the like. We definitely delve into that a bit as well. So anyways, customization in research. This is where open source also shines. It can help develop innovative solutions and personalized AI assistants. They can use natural language processing libraries like GPT-3 or GPT-4, I believe just dropped, allowing users to customize the behavior and responses of these virtual assistants to meet their specific needs. And so can I access these slides? I will have to see about that. But if you are in the MLH Discord, definitely send me a message and I can communicate with you on that. Does data security can also be linked with cybersecurity as a field? Yes, certainly. So that's the thing, these things don't exist within a bubble. In the real world, you have all sorts of overlaps with all sorts of different areas of, well, anything you can imagine, really. Like, for example, front-end web development. If you have statistics that you want to display online from your data science search, then there you go, right? You can hook up, and I'm sure you could use React that could do some data science processing that you could hook it up to, I don't know, whatever React-based tools there are for that. I'm sure there's lots of JavaScript libraries in that domain. which you can use to feed your front-end interface that displays on your website. So definitely, I would say definitely think about that. Think about how these different areas of tech, programming, data science as a whole could naturally intersect at different points. Okay, transparency, honestly, I think we're okay with that. In fact, I think some of these aspects will be a little bit more interesting once we get to talking about data science more as a fundamental area, because we kind of get the gist of it now. It's a little bit undecided on how I wanted to structure this, but now as I'm going through this, things are starting to crystallize a lot more. But anyways, I hope this has at least been given some insight to you all as of this point. If there's anything that so far that's struck you, I'm curious what that would be. Anyways, we can start with something a little bit more. Here, let's see. Oh, got more in the chat. Oh, AWS. So if I'm interested in these multiple fields, what do I do to gain knowledge without losing focus in either? Right, so that's a pretty good question. Well, I guess that's kind of the issue of opportunity costs. So the idea of opportunity cost, essentially, is that the time that you spend doing something, you can never get that time back, right? It's just gone. It's in the past. So what could you have possibly been doing with that time that you didn't do with it in the end? What did you lose that time on, quote unquote? I don't like to say the word lose because it makes it kind of implies that it's a waste, but obviously once your time is used, it's gone. So with how you spend that time, if I spent all of my life studying front-end web development and I'm at my 11th hour, it's probably a little bit too late to go all the way back and start in data science, right? It's a pretty extreme example, but we're faced with opportunity cost in our everyday life, even on a much smaller scale than the entirety of your lifetime. So in terms of where do you gain knowledge without losing focus in either, I would say be wary of opportunity cost. You want to have a process of elimination if you can, as a result. So, for example, if you think you might be interested in, I'm just going to say front-end web development or data science, or let's say UI UX design, what do? Dabble a little bit in each, kind of get a taste of them, get a feel what they're all about. And usually a good pathway is seeing which one resonates with you the most, or which ones resonate with you fairly strongly at the very least. So the ones that resonate with you are usually the ones that you can, they're usually a pretty safe bet to pursue. Now, there's quite a few other things to keep in mind as well. Like I think for most people, they also want to keep in mind the sort of salary that they could make, the sort of employability, how in demand that field is, and the growth of that field over time. All important things to keep in mind as well. But ultimately, you take these aspects, you take these different areas that you're interested in, get a feel for each of them, try your hand out with them, because you don't know if you're going to like UI, UX design. You don't know if you're going to like data science. You don't know if you're going to like front-end web development, for example. The only way that you can possibly get a better understanding of how they relate to you and what they could hold in your future is if you try and embark on them at least a little bit to kind of get a sense of what they're about. So if you tackle them and you like them all, or maybe you don't like them all, maybe you can talk, maybe you don't like UI UX, you can focus on front-end development and data science, or maybe you only like the other two. Maybe you like all three, maybe you don't like any of them. It's nice because it helps you focus on where you actually need to focus then in terms of where to put the majority of your time and the like. So let's say you have two areas that you want to focus on. So let's say data science and front-end web development, whatever they are. Spend more time with them, go in deeper with them. You might realize that you only want to focus on one. You might realize that you want to specialize heavily in one and have some ancillary knowledge in the other. What a lot of people recommend overall that I've talked to, that I've read about, and what I've experienced myself is having a T-shaped skill set where you can imagine an uppercase T, where you have this very shallow but wide expanding base, and then you have that one thread that digs deeper, deeper, and deeper all the way down. So that one thread is your specialization. That's where you're going to spend the most of your time, have the most deep expertise in. But you don't just want that one area of knowledge, because, well, for quite a few reasons, honestly. One is maybe that's not the thing that actually makes you tick, or maybe you'll get burned out on it. But I mean, let's imagine that it is that place that you want to go to. It could possibly be that. I'm trying to think of how to articulate it in the moment. Essentially, you need a specialization to be to achieve the highest that you can in terms of your career and profession. Typically, you don't want to only have knowledge in that one hyper-focused domain, because that just sort of limits you. And there's different areas of related study and of related knowledge that can really bolster your overall skill set. So it's a good idea to delve into some of those things. Like for example, like if you're doing data science, probably wouldn't hurt you to understand a bit more about how algorithms and the like work. It can help you to understand how to create more effective and efficient solutions for your data modeling and the like. If I'm using this terminology right, again, I'm still fairly new to the world of data science myself. Or two, if you work at a company and you're going to put these sort of statistics and whatever insights that you gain out onto, like, say you're very focused on the web and user interaction with the web. Probably wouldn't hurt to learn a little bit about how the front end works on a website, and principles of UI and UX of how users can access your data. That way you can learn how to present it and gather it in a way that is digestible for users and that they can more readily contend with and understand. So I hope that gives some insight as to, because yeah, that's kind of the overall thing. It's like, definitely explore different areas, pursue those that seem meaningful, but usually you're going to have one thing that you specialize in. Just pursue that fully. And I mean, honestly, I think overall, just the last point on this talk is that as long as you strive to make forward progress, things will sort themselves out. A lot of people, they'll get afraid, or they'll just kind of get paralyzed. Like, okay, I don't want to do the wrong thing. I don't want to do the wrong thing. Or I don't want to put so much time into this thing, but it turns out I don't want to do that in the end. What ends up happening with some of those people is that they just don't do anything as a result. So they don't grow anywhere. It's so much more fruitful to just pursue something that seems meaningful in any sort of particular sense, to any sort of degree. By doing that, things get clarified. You get a better understanding of what's possible and what resonates with you, and you build competence overall. So very, very important thing to do. Never be stagnant. Always be striving to make progress, even if it's not in the area that you'll ultimately pursue mainly. So with that, my laptop battery is freaking out right now. Give me 1 second to plug this guy in. So should I study data science fundamentals? If I want to go into AI and machine learning, would it be better than just jumping straight into an AI intro course? Well, let's talk about that in just 1 second. That I can't answer in good conscience, just because because I'm just not so deeply embedded within data science or like AI and machine learning. I would talk to someone a bit more experienced about that. Just to be frank, I don't want to give you bad advice. But I know that there are some beginner resources for things like AI and machine learning. I know that if you're familiar with the CS50 courses put on by Harvard, there's these free online courses that delve into areas of computer science. They actually released one recently on AI. It's Intro to Artificial Intelligence with Python. I'll post that in the chat for you here. It does recommend, so there's the CS50 course, which is Intro to Computer Science. It does recommend that as a prerequisite, but again, that's free in and of itself. I'll post a link here for you. The cs50.harvard.edu/AI/2023. And through it, it'll just be an exploration, as it says, concepts and algorithms, the foundation of modern artificial intelligence. So there's something to explore at the very least. But yeah, I know there's lots of like intro to data science with Python courses as well. Python seems to be a solid tool to explore data science with. That's actually what I'm doing myself. I'm teaching myself Python at the moment, so I can get into. I'm not going to be pursuing data science professionally, at least as far as I know right now. But I would like to learn basics of data analysis and analytics for engineering. So yeah. So I guess definitely seek out intro to data science, fundamentals data science. Look into these intro to AI. I mean, it says intro to AI, so maybe it's more introductory. But yeah, ultimately, I seek out resources with people a little bit more learned on that aspect of things. Okay, we have some other questions in the chat. How can I contribute to open source and data science if I'm new at everything? So you just finished a data science boot camp, but you're fairly new to programming and open source as a whole. There are some resources for that. I will drop them to you guys right now, in fact. Let me see. I have the links here. I think I might have them in this slide, actually. Let me see. Let's skip ahead a bit. Boom, 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 boom. No, okay. I'll have to find them then. I know I have them in here somewhere. That or it's in my notes document that I drafted up. Yeah, I'll have to find that for you. But with that, there's all sorts of resources for getting beginners inundated into data science or into open source tools overall. Like there's let me see if I have this. College for data science outline. Otherwise, maybe I can share them in the Discord afterwards. Nope. Anyways, I'll find them near more towards the end. I don't want to hold up the overall stream on that. But definitely a good question. Just know that they're actually out there. We'll talk about that more towards the end of the talk. So yes, you have to try everything at the beginning to see what we're really interested in. Honestly, that's what I'm doing right now to an extent. So I know that I want to do things with software and programming. And I thought I was going to be interested solely in that and doing like software development. But after playing around with Arduinos and learning more about physics and the like, I've taken an interest in engineering. I'm undecided if I want to do electrical engineering or mechanical engineering. I know that I want to heavily include software with those to the point where, to the point where I could use it professionally. Software is crazy tool to have in your toolkit. But with that, what do? I'm just going to explore more each. I'm going to take some intro classes for both electrical topics and mechanics focused topics like statics. Do some personal projects. I'm working with Arduinos right now. I'm going to be starting some mechanical focused projects soon, or maybe just like pure Newtonian physics stuff, and see which one resonates with me more. And from there, I can get a better idea of where I want to focus. I already have a very big background in software engineering and programming, so I could only have gotten that. I could have only have learned that those were things that I wanted to pursue by jumping into that and just working my butt off in terms of learning and exposing myself to different contexts within it. I learned that while I did web development for about a year and I got fairly decent at it, I learned that it just wasn't what I wanted to do. Was it a waste of time? No, not in my opinion. Because I learned all sorts of things about software development, and I can easily translate them to other areas of programming that I'm interested in, like, again, working with these hardware systems. So, again, as long as you strive for competence and strive for understanding more of yourself in terms of how you interface with the within your interests and skills and the like, that you can interface with the, I guess ideally with the professional world and the like, because I think a lot of us are doing this to get an education, to get a career, then that is, I think that's the most powerful thing that you can do. So currently finishing CS50X right now. Yes, the AI one is fairly new as far as I know. I don't know when they posted it, but I only recently learned of it myself. So pretty crazy. I think they uploaded a video on YouTube for it. CS50 presents. Was it? Okay, well, the video was uploaded 3 years ago, so I guess not relatively new, but here we go. Okay, so anyways, lots of good questions. I'd actually love to talk about this stuff all night. Well, I mean, we're going to cover some more about the intro to data science, though, too, of course. But if you guys have any more questions, definitely throw them in. I think this sort of discussion is very helpful. But anywho, with this, I want to talk a little bit more on the meat of data science in and of itself. I had more of a larger overview at the beginning, just kind of covering like why data science is used and how different aspects of using certain tools, like some of those open source tools, like the NumPy and scikit-learn for Python, some of the benefits that they bring. But we're almost an hour in at this point, so I want to get more into the meat of data science itself, just as a discipline. So with that, well, we have data sets and workflow. Yeah, I guess we can focus on workflow first. That seems fine. Again, it's a little bit more of the large form, but I think it's pretty important. So workflow solutions provide a structured approach to managing data-related tasks and streamlining the data science process. Various data science tools can be effectively utilized in various stages of the data science workflow, allowing the creation of end-to-end data science pipelines. So, for example, never mind. So, for example, a structured approach. Workflow solutions offer a structured framework for data science projects, helping them stay organized and focused on the tasks at hand. This is especially beneficial. I mean, this is beneficial for everyone, but for aspiring data scientists who are learning the ropes of data science methodology, definitely helps to have an organized system in place to keep you in the lane of proper possibility. Another aspect of workflow, applicability and sharing. So workflow solutions facilitate the replication of data science experiments. Individuals can easily share their work with colleagues, classmates, or the broader data science community, promoting transparency and collaborative learning. So there's Jupyter Notebooks and Git repositories can be used to create and share reproducible data science projects, for example. Workflow helps with efficiency and productivity. They streamline data-related tasks and processes, allowing us to operate efficiently. By automating data acquisition, cleaning, analysis, and reporting, it allows us to allocate more time and resources to strategic decision-making with these data science projects. I mean, especially for like bigger organizations like startups or corporations or the like. There's the aspect of scalability that workflow helps contribute to. Scalable workflow solutions ensure that data science operations will scale seamlessly. By using management systems, corporations or larger organizations, what have you, can handle increasing data volumes and complex data processing requirements without overhauling their existing infrastructure. And then with workflow too, if we really want to get into the big leagues, there's stuff like data governance, where large enterprises must maintain strict data governance and compliance standards. Workflow solutions offer centralized management of data pipelines, making it easier to enforce data governance policies and ensure that data is handled responsibly and securely. And two, there's interoperability, where large enterprises often have diverse data sources and systems. Workflow solutions allow for the seamless integration of open source components and legacy systems, or any other sorts of areas of integration of outside systems, you could say. So this flexibility ensures that data science pipelines can be designed to work with a variety of data sources and platforms, including databases, cloud services, and on-premises systems. Okay, let's see, we got some stuff in the chat here. So already in 5th semester, try to explore more until this year ends at least. So computer science and engineering. I'm curious, what exactly does that cover, your coursework, computer science and engineering? Is that you study computer science and you study computer engineering? I would imagine so, but just curious. Will they be a part 2 live? No part 2 to this, but we have our MLH Discords and community hubs that you guys can more than welcome to ask questions or continue this sort of discussion on there as well. So what if I'm interested in machine learning and deep learning? Should I learn more into CS or data science? I mean, I'd imagine that machine learning and deep learning, they both have different areas of them where CS would be more useful or where data science would be more useful. Like in designing the software in and of themselves, I imagine CS plays a very big role in terms of understanding the data processing and cleansing and organization and all of that. I'm sure data science would be the one for that. So, I mean, it's good. This seems like a conundrum, but it's actually good because it seems that you've been able to, again, do a process of elimination of sorts where you realize, okay, I'm interested in machine learning and deep learning. Where do I go from here? Now, again, just more process of elimination. See which side of things interests you more. Are you more interested in the CS side? Or are you more interested in the data science side? How can you figure that out? Now, just, again, try to approach this subject, machine learning and deep learning, from those different angles. Try them out. So there are intro to data science courses. There's intro to CS courses. There's intro to just machine learning and deep learning courses as well. So that CS pathway might be pretty good for you. That in terms of not overall, but in terms of that Harvard course is what I wanted to say. That Harvard course you could pursue, because there's the Intro to Data Science course, or Intro to Computer Science course that it offers, CS50X, and then there's the AI one, which naturally builds upon that. So you'll get a bit of a taste of computer science, and then you'll get a bit of a taste of computer science as applied to AI. So check that out, possibly. So wouldn't data science essentially fall under computer science? I'm not entirely sure of that, like in terms of the most grand scheme of things. There can certainly be a lot of overlap, especially in how it's actually utilized nowadays. But there's some people that go like the pure statistics route, and they when they come into something like data science, I'm sure they have a much different perspective. Maybe a much different perspective than someone that has like a pure programming background. But again, I'm not too educated on this sort of stuff, so I can't really give too much insight or advice. It looks like we have people in the chat giving some insight. So we study basics of C, Python. Actually, I chose data science as my specialization, so this semester I'll get to learn basics of R programming and data analytics. Okay, cool. So it's quite different here in computer science engineering. We start out few of the starting semesters with engineering, and then we get to choose which specific field of computer science are we going to according to our interests. So is it like are we going to according to our interests? So I would imagine that ideally you find a field of engineering that you like, and then you start to work concepts and areas of computer science into it, or are they kind of treated as separate? So in terms of wouldn't data science essentially fall under computer science? It's one of the many specializations along with AI, machine learning, web dev, so on and so forth. Yeah, so definitely do your own research on all this too, and talk to people that do this sort of stuff for a living, or that are just infinitely more experienced than either you or me. I'm sure they can give a lot of pertinent insight. But anywho, on this aspect of workflow, we kind of covered the main aspects of it. But ultimately, workflow solutions in data science offer structure, efficiency, and scalability. These solutions enable the creation of end-to-end data science pipelines, ensuring that data-related tasks are organized, efficient, and compliant with data governance standards, too, especially for those basically relevant for like those larger organizations and the like. But these sorts of tools play a vital role in building and customizing these workflows, making them accessible to a broad range of users in the data science community. So let's go a little bit on to data sets. So again, more of the fundamentals of just pure raw data science, things to know. Data sets provide the raw material that data scientists work with to conduct analysis, develop models, and derive insights. They are collections of structured or unstructured data, representing observations, measurements, or records of a particular domain or problem. Data sets are essential for training and testing machine learning models, conducting statistical analysis, and performing various data-driven tasks. So data science benefits significantly from the availability of diverse and publicly accessible data sets, which facilitate research, experimentation, and the development of data-driven solutions. Some of the key aspects of data sets are data types. So data sets can contain a wide variety of data types, including numeric data, categorical data, text, images, audio, and more. The nature of the problem and the data available determine the types of data sets used. Another key aspect of data sets are structured versus unstructured. So data sets can be structured, as in like tabular data with rows and columns, or unstructured, text documents, images, audio recordings. Structured data is typically easier to work with, while unstructured data often requires pre-processing. Features and labels. Data sets often consist of features, independent variables, and labels, dependent variables. In supervised learning, features are used to predict labels. For instance, in a dataset of housing prices, features might include square footage, the number of bedrooms, and location, while the label would be the price. Actually, bit of an aside, I just remembered a great resource that you guys would definitely find interesting. So there's this website called roadmap.sh, and it lays out all the sorts of concepts that a person would need to know to study various aspects of different areas of tech. So let me share my screen here and show you what I'm talking about. So roadmap.sh, I'll drop the link in here. There's different roadmaps for different types of, these are role-based roadmaps, so front end, back ends. I swear they have data science somewhere along here. For skill-based roadmaps, best practices, do they have data science? Data scientist, here we go. AI and data scientist. So this roadmap was created by the AI and data science team at Careem, which is an Uber company. Interesting. So that's a pretty good source to get your information from, to say the least. Oh yeah, look at that math. Okay, linear. I like how the first step is differential calculus and linear algebra mathematical analysis. So definitely gives some great insight there. Go to statistics, hypothesis testing, probability and sampling. Yeah, this is definitely stuff I've not heard of. I've not delved into this this intensely at all. But then again, I'm not going for data science in terms of my profession or for anything to do with AI. So it makes sense as to why I wouldn't be familiar with this. Exploratory data analysis, coding. Here we go. Here's some coding stuff. So the site also has a roadmap for Python too, actually. But yeah, it's recommending Python, data structures, algorithms, and Python. Interesting. SQL, visualization. Okay, so here we go. Machine learning, deep learning. So if you want to go on the self-taught route, or I mean, not fully self-taught, maybe you could, I don't know. But anyways, this should definitely give some good perspective on the sorts of skills and the like that you should need. Because again, this was put together by a team at Uber of AI and data scientists. So they would know much more than the average person, that's for sure. Okay, a little bit more discussion in the chat. So, okay, so we had that with engineering. So in the first year, we learn electrical, mechanical, and other engineering stuff. And then from second and third year, we choose either we're taking AI, machine learning, or data science, blockchain, or cybersecurity, stuff like that. That is pretty interesting. So does it all come together in the end? Like if you start with electrical engineering and then you ultimately go into or say you do mechanical engineering and you ultimately go into, say, like the blockchain, how does that overlap exactly? Is it expected to? Because those are two fields where they might not have too much to do with each other, at least in terms of unless you really try to specialize in a niche where the two intersect. Pretty similar at your school, okay, Strata. So in that data mining course, they made it clear that adjusting coded data sets, data set hygiene, cleaning out bad data, adjusting field names and structure, and in general, wrangling data sets into the right format was a huge part of this problem space. Okay, definitely makes sense. Yeah, and two, again, that's one of the first things that we're tackling and what we're going over right now in terms of the fundamentals of data science. To do data science, you need data. Who would have thought? So learning about the type of data, how that data is organized, so on and so forth, pretty fundamental. Okay, so anywho, there's this resource which would be pretty informative for you all. But again, like, this is saying to start with all sorts of intense math and statistics. Probably don't have to, in terms of just getting a taste for what this is all about. Again, there's, like, if you go online, there's intro to data science courses with Python that I imagine don't require too heavy of a math background. But again, if you just want to get a bit of a feel for things before you decide you want to jump in and get your math up to these levels, might be worthwhile doing that as well. But with that, let's jump back to some of these fundamentals here. So some of these more key aspects. So we talked about features and labels. We also have data size. So data sets can vary in size from small data sets used for experimentation to large data sets, often referred to as big data, which require distributed processing. And finally, our final key aspect is data sources. Data sets can be sourced from various places, such as public repositories, data marketplaces, APIs, web scraping, sensors, and more. So in open source data science, we've had some interest in this, in fact, tonight. So I don't know if it's too relevant as of right now, but those are just some of those key aspects. So in all, data sets are the lifeblood of data science, and it thrives on the availability of, some areas of it thrive on the availability of diverse and accessible data sets. They provide the foundation for research, experimentation, learning, and the development of data-driven solutions across various domains. So let's go on to our next aspect of the fundamentals of data science, data engineering. Data engineering focuses on the collection, transformation, storage, and preparation of data for analysis. Makes sense. You have your data, you have it, you have data, and now you need to get it in order. You need to possibly clean it up. You need to possibly organize it in a way that's meaningful, not just in and of itself, but that's meaningful for the task at hand, whatever it is that you're trying to gain insight on, from whatever perspective. So data engineering encompasses the processes and tools used to acquire, clean, and organize data, making it ready for analysis and machine learning. So some of the key aspects here. Data pipeline is kind of the big thing here. Data pipelines are a series of data processing steps that involve collecting, transforming, and moving data from source to destination. Data pipelines are designed to automate the flow of data, ensuring that it is reliably and efficiently processed, stored, and made available for analysis, reporting, or other purposes. So we can go into data pipeline a little bit, some of these different steps, or just picking apart the different steps in this series of steps. First would be data collection. So data pipelines start with the sources of data, as we kind of talked about before with our data sets. Well, not even yet, just getting the raw data even in and of itself. These sources can include databases, APIs, log files, sensors, and external data sets. Sources can be both structured, like databases, and unstructured, like text files or images. Next, it brings us to extract, transform, and load processes, which are designed to extract data from source systems, transform it into a usable format, and load it into a data store or data warehouse. Hence the name, extract, transform, load. For the extract part, data extraction phase involves retrieving data from these sorts of sources that we talked about. It may require connecting to databases, making API requests, or ingesting data from file systems. Transformation. After extraction, the data is involved in a raw, or is often in a raw or unstructured form. The transformation phase involves cleaning, enriching, and structuring the data, which includes handling missing values, outliers, and inconsistencies. Integration involves merging data from multiple sources and resolving schema conflicts to create a unified data set. So transformation ultimately ensures data quality and integrity. It standardizes data formats and performs calculations or aggregations as needed. And finally, of the extract, transformation, load processes. When it comes to loading, once the data is transformed, it needs to be loaded into a storage or data repository. Data can be stored in various data stores, including data warehouses, data lakes, and cloud storage solutions. So just keep my eye on the chat here. So for undergrad, be an engineering specialty. Okay, interesting. Interesting how schools do that. So in terms of the data pipeline, we talked about collection. For data storage, this is where data warehousing and data lakes come in. So a data warehouse, for data warehousing, data engineers design and maintain data warehouses, which are optimized for storing and curing structured data. Data lakes are for handling large volumes of structured and unstructured data. For data processing, our next point here, data pipelines can be designed for batch processing or real-time processing. For batch processing, data is, did I slide on this actually? No. For batch processing, data is collected and processed in chunks at specified intervals. So there's pros and cons to both batch processing and real-time processing. For batch processing, some of the code or some of the pros are efficiency. So batch processing is efficient for large-scale data processing because it reduces the overhead of handling data continuously. It allows for optimizations like parallel processing. It's cost-effective because resources can be allocated during specific processing windows, reducing the need for constant monitoring and real-time infrastructure. It has high throughputs. Batch processing can process and analyze large volumes of data, making it suitable for historical data analysis and generating periodic reports. There's scalability. Batch processing can be scaled by increasing the processing capacity or parallelism, making it adaptable to growing data volumes. And there's also error handling. Errors are easier to manage in batch processing because issues can be identified and addressed at the end of the processing window. Some of the cons of batch processing are latency. Since data is processed in scheduled intervals, latency is naturally introduced, which may not be suitable for real-time decision making. It can also lead to stale data, and batch processing data is typically outdated by the time it is processed, which may not be ideal for applications requiring real-time insights. And finally, designing and managing batch processes can be complex, especially for near real-time requirements. But in terms of your use cases for batch processing, it's great for historical analysis. So when historical analysis of data is required, such as generating daily, weekly, or monthly reports, batch processing is a perfect solution. For resource efficiency, batch processing is suitable when optimizing resource usage and reducing the cost of real-time infrastructure when that's a priority. And for scalability, it's a good choice when handling large data volumes and when you need to scale horizontally. So that is batch processing, the best and the worst, and where it's suited for. Now, real-time processing, it involves the immediate analysis and response to data as it is generated or received. Some of the pros of real-time processing includes low latency. It enables the low latency data analysis, making it suitable for applications that require immediate decision-making, such as fraud detection and recommendation engines. It offers up-to-date insights, allowing organizations or whoever to react quickly to changing conditions and make real-time adjustments. Continuous monitoring. Real-time processing supports continuous monitoring of data streams, helping to identify issues and opportunities as they occur. Streamlined processing. Real-time data can be ingested and processed without the need for storage, which simplifies data pipelines. Those are the pros. As for the cons, there's complexity. As real-time data processing is complex, it often requires sophisticated infrastructure and management. It's resource intensive, requiring dedicated infrastructure to handle high data velocities, and it tends to lead to higher costs due to infrastructure, data processing, and monitoring. For use cases of real-time processing, best for immediate data or best for immediate decision making. So when immediate decision making and rapid responses to data events are critical, this is a perfect solution, such as in finance, trading, real-time bidding, and sensor data processing. It's good for continuous monitoring. If you have to monitor data streams to detect anomalies, performance issues, or security threats, also a solid choice. And for streaming analytics. So for applications that rely on streaming analytics, such as recommendations, personalizations, and IoT applications. So ultimately, the choice between batch processing and real-time processing really depends on the specific needs of the data-driven application. In many cases, a combination of both approaches, often referred to as Lambda or Kappa architectures, is used to achieve the benefits of both batch and real-time processing. Honestly, that's just kind of how reality lays itself out in my experience. The world is a complex place, and problems are often very context-specific. There could be multiple types of solutions that exist for a particular domain. Usually best to understand how to utilize them for any varying degree for any particular problem in order to efficiently solve it and just to best solve it overall, whatever your goal is. So isn't batch processing also used as an operating system concept too, as these techniques for data science taken from there? Honestly, not sure. I haven't studied operating systems yet. Definitely would be an interesting thing to explore and see. At the very least, if there is a meaningful, even if you have the conceptual linkage that you have now, I'm sure it can lead you down some pretty interesting pathways if you explore it. So let's see. Analytics. So what else? Okay. So we tackled the batch processings and the like. So we're still on data pipelines just because it's such a fundamental aspect of data engineering. So next is monitoring and management. Data pipelines require monitoring and management to ensure data quality, detect and handle errors, and track pipeline performance. Data engineers implement data validation checks to ensure data quality and consistency. Next is data governance and security. So data engineers implement data security measures to protect sensitive information. And there's also metadata management tools that can help document and track data lineage and metadata. So for data pipelines overall, the benefits to them, taking the essence of those steps and how they fit into the overall area of data science, and now understanding how they can be utilized to benefit data science as a whole in terms of the benefits of data pipelines. They lead to efficiency. Data pipelines automate the process of data collection, transformation, and loading, reducing manual effort and minimizing errors. They offer consistency. They ensure that data processing steps are consistently applied, leading to standardized data. Scalability. Data pipelines can be scaled horizontally to accommodate growing data volumes and processing requirements. Reliability. Data pipelines are designed for reliability and fault tolerance, allowing for the processing of large data sets without data loss. Real-time insights. Real-time data pipelines enable organizations to react to data quickly, facilitating real-time decision-making and analytics. Historical analysis. Batch data pipelines are essential for historical data analysis, allowing organizations to understand trends and patterns over time. And again, data governance. Data pipelines often incorporate data governance and security measures to protect data and ensure compliance with regulations. So data pipelines are crucial in modern data-driven organizations as they provide a structured and automated approach to data processing, ensuring that data is ready for analysis and decision-making. Open source tools and frameworks play a vital role in building and managing data pipelines, making them accessible and cost-effective for organizations of all sizes. So in terms of augmenting data engineering stuff, there's quite a few different things that you can do. Let's see. Or overall, honestly, let's just jump into data visualization of all things. Data visualization is, well, I guess on that note, are there any questions or insights on the aspects of data engineering and the data pipeline, how it fits into those? Just curious. But with that, we can move on to data visualization. So quite an important area of data science, or really just a crucial component of data science. Data visualization involves the representation of data in graphical or visual formats to help people understand complex data and make data-driven decisions. Effective data visualization enhances data exploration, analysis, and communication, making it an integral part of the data science workflow. So we're now going to cover some key aspects of data visualization. First is data exploration. Data visualization begins with the exploration of the data set. So libraries like Pandas and Matplotlib and Python, like we talked about before, allow data scientists to quickly generate various types of plots, such as histograms, scatter plots, and box plots, to gain insights into the data's distribution and patterns. There's also pattern identification. Visualizations help in identifying patterns, trends, and anomalies in the data. For example, line charts can show temporal trends, while heat maps can reveal correlations and clusters in data. Feature engineering. Data visualization aids in that, which is a critical step in machine learning. It helps select relevant features and transform them effectively for model training. So there's tools like Seaborn, which provide specialized plots for feature analysis. Another key aspect is model evaluation. During the model evaluation phase, certain solutions like scikit-learn offer libraries for creating various plots, including fusion matrices, ROC curves, and precision recall curves to assess the performance of machine learning models. So again, this kind of ties heavily into some of the interested people here in chat. And lastly, for interactive dashboards, certain libraries like Plotly enable the creation of interactive dashboards and web-based visualizations. These are valuable for communicating insights and analyses in an engaging and customizable way. Just like I was talking about earlier with front-end web dev, right? People, when you think data science, you don't typically think of front-end web dev as well. But as we said, there's certainly ways, there's certainly areas where you can have the two intermingle and even possibly feel a professional niche. So give me 1 second, let me get my water. Just right off here to the side. But yes, data visualization. Again, these are pretty fundamental aspects. I really hope the intro to data science part kind of comes across in the way of covering these most fundamental principles of how to approach this subject. I don't know, because like visualization doesn't seem that technical. Doesn't seem like the most, I don't know how to articulate it exactly, but so powerful in terms of just building your intuition and building your understanding and of the field overall, and two, even with communicating with both professionals and those not involved in the data science. There's benefits of it in open source, because usually I have a lot of people interested in open source. If anyone's curious on that, just let me know. I can go on more detail. But with that, so we talked about data sets, we talked about data engineering and the data pipeline, how that ties into it. And here we have data visualization. Once you have your data all nice and neat and proper, you can finally put it out into the world. Another area is machine learning. Machine learning focuses on developing algorithms and models that enable computers to learn from data, make predictions or decisions, and improve their performance over time. It plays a significant role in extracting valuable insights, automating tasks, and solving complex problems using data. Machine learning is highly relevant to data science as a whole, and there are many solutions and libraries providing the tools and frameworks needed to develop and deploy machine learning models effectively. So some of these key concepts are, well, data, of course. Data is the foundation of machine learning. It can be structured, unstructured, or semi-structured, and is used for training, validating, and testing machine learning models. Features. Features are the attributes or variables within the data that are used to make predictions or classifications. Feature engineering is the process of selecting, transforming, and engineering these attributes. Labels. Labels are the target variables that machine learning models aim to predict. In supervised learning, models are trained on data with known labels. Algorithms. Machine learning algorithms are mathematical models or techniques that enable computers to learn patterns, relationships, and rules from data. So some of the common algorithms that you'll come across include linear regression, decision trees, random forests, support vector machines, and neural networks. There's training. So training a machine learning model involves feeding it with labeled data to learn patterns and relationships. The model adjusts its parameters to minimize the difference between predicted and actual labels. And finally, testing and evaluation. After training, models are tested on new, unseen data to evaluate their performance. Common evaluation metrics include accuracy, precision, recall, F1 score, and a mean squared error. As for the types of machine learning, there's supervised learning, where models are trained on labeled data, and their goal is to predict labels for new, unseen data. It's used for tasks like classification and regression. Unsupervised learning, which involves clustering and dimensionality reduction. Models aim to discover patterns and relationships in the data without labeled examples. Semi-supervised learning, this combines elements of both supervised and unsupervised learning, using a small amount of labeled data along with a larger amount of unlabeled data. And then there is reinforcement learning, where agents learn to make a sequence of decisions to maximize a reward. It's used in applications like gaming, robotics, and autonomous systems. So we have some on data science or open source, but not really sure if that's our interest. Rather focus more on the fundamentals here. Helpful, but I gotta get some sleep. Yeah, thank you for stopping by. Always appreciate it. Yeah, we have some people tuning in from pretty late hours into the night, just time zone differences. But anywho, so we were talking a bit before about how data science ties into other areas of tech, if it does in the first place, which it certainly does. As we saw, for UI UX, you have the whole field of data visualization. For front-end development, that too also goes into data visualization. And data science with fields like cybersecurity, definitely a big area there. Here we have an entire slide on it. So for privacy and security, they address the protection of sensitive and confidential data, as well as the safeguarding of data-driven systems and models from potential threats and breaches. The relevance of privacy and security in open source data science is essential, as data-driven projects often involve the handling and processing of data that may be sensitive or confidential. So for privacy, a few different aspects to talk about, such as data collection and handling. Data scientists must ensure that data collected and used in projects respects individual privacy. This includes obtaining proper consents, anonymizing or de-identifying data when necessary, and complying with data protection laws, such as General Data Protection Regulation. Also, data masking and anonymization. Anonymization techniques are used to protect privacy as well. There's certain tools like Python libraries like Faker and databases like, Postgres, SQL, something like that. Offer features to generate synthetic data or pseudonyms for privacy-preserving data analysis. There's differential privacy, which is a formal framework for preserving privacy in data analysis. There exist tools, libraries for implementing differential privacy in data science projects. Data sharing and collaboration. So when collaborating on data science projects, sharing data with other contributors should be done securely. Encryption and access controls are essential to protect data privacy. And finally, transparency. Maintaining transparency about data usage and privacy practices is crucial. Data scientists should document the data sources, handling procedures and privacy considerations in their projects. There's also security, with a few aspects for us to talk about in that domain. There's model security. The models developed in data science projects can be vulnerable to adversarial attacks. Ensuring the security of machine learning models is essential to prevent tampering or malicious exploitation. There is data storage. Data storage systems should be secured against unauthorized access. Encryption, access controls, and strong authentication methods should be used to protect data at rest. Data transmission. When data is transmitted between systems or over networks, it should be encrypted to prevent eavesdropping. Secure protocols like HTTPS and SSH should be employed. API and security. So data science often involves, it can often involve external APIs. Secure API key management and validation are critical to prevent unauthorized access. There's also code security. Code can introduce security risks. Data scientists should ensure that the code used in their projects, including open source libraries, is regularly updated and free from known vulnerabilities. Secure environments. Data scientists should work in secure computing environments and follow best practices for system security. Virtual environments, containers, and cloud security measures should be considered. For access control, access to data systems and models should be controlled and limited to authorized personnel only. So can involve basically implement role-based access control where applicable. And more open source stuff, but let's go into challenges and considerations. So there's certain challenges and considerations that data scientists, organizations, and data science communities should be aware of. So there's quite a few that we can cover. Let me check the chat real quick. It's 5 a.m. now. Are you up early or are you staying up late? That's one of those hours where it's like you can never tell. So for data privacy and security, which you talked on a bit just now, data science tools and libraries may not provide built-in data security features. Data scientists and organizations need to ensure that sensitive, confidential data is properly protected. Another challenge is data quality and reliability. Data sets and libraries can vary in quality, accuracy, and reliability. Data scientists must carefully evaluate the data sources and be prepared to clean and pre-process data to ensure its quality. There's community support. So especially for open source tools and libraries, relying on open source may mean limited official support. So data scientists often depend on community-driven forums and resources for troubleshooting and problem solving. Documentation for, I don't want to say this. Creating documentation is a task in and of itself. Lacking comprehensive documentation can make it challenging for new users to understand and use tools effectively. There's aspects of integration and compatibility. We've touched on it a few times throughout this here and there. So ensuring that data science tools and libraries work well together and integrate with existing software systems can be challenging. Compatibility issues may arise. There is especially a need for this, it seems, in legacy systems. Like we talked about, you'll often see those at big companies or financial institutions, so on and so forth. Version control. So managing different versions of software and libraries can be complex. Keeping tools up to date and managing dependencies requires careful attention. There's licensing and legal considerations, especially, again, more for like open source type stuff. Scalability and performance. depending on some of these different libraries and the like, they may not be optimized for high performance computing for as like proprietary solutions maybe. So organizations dealing with big data may need to address scalability and performance issues in their solutions. And then some, so those are some challenges, some considerations. And then again, data governance, we talked on this a little bit already, a few points. Organizations need to establish clear data governance policies when working with data science tools to ensure data quality, security, and compliance with regulations. There's training and skill development. Data scientists and teams must invest time in learning and mastering tools and libraries. Training and skill development are essential to make the most of these resources as a result. Community involvement, especially for those participating in open source communities. Contributing to projects or reporting issues helps improve the tools and ensures they remain relevant and well maintained. So organizations must plan for ongoing support and maintenance of tools, especially those customized ones like we had with Uber or with open source tools. This includes keeping software up to date, addressing issues, and ensuring compatibility with evolving technologies. And these other ones, again, these are more for like once you're kind of already into the business side of things, not too much for us folks here. I think we already talked enough on them. Let's get to this last point, the data science workflow. So data scientists should design and optimize their workflows around their tooling. This involves integrating tools, version control, and choosing appropriate libraries for specific tasks. So overall, quite a number of challenges and considerations to take into account. Definitely not exhaustive here, but just kind of gives a bit of a taste as to all that involved. So lastly, I thought it would be fun to go over some instances of how data science was applied to the world here, or into, I don't want to say, because obviously data science should be applied to the world overall. Well, some people just do it in and of itself too. I guess there's just the thrill of the game in and of itself. But in terms of seeing data science applied towards real world problems and offer genuine solutions, we'll take the rest of this to kind of go through some of these. So you were at 5 a.m. staying up late. There we go. You're on the grind. Love that. Well, I have a few different skill sets. Tech is actually not my first career, but my first career, I was so crazy into the subject matter and what I was studying, what I was teaching myself, I would spend at least 12 hours every day just learning, practicing, making my own projects. Did that I must have kept that up for at least a year, about 12 hours every day. I don't know. You definitely need a balance of work and life, but if you're hungry for this sort of information, that's definitely good. Basically, if I had to put it into one phrase, to one main point, you could be doing worse things at 5 a.m. Definitely a good way to spend your time. So anyways, let's get to some of these case studies and examples. So for COVID data analysis, in fact, some of these have quite a bit of open source overlap. For COVID data analysis, the open source data science community actually played a pretty significant role in analyzing the COVID data. They created dashboards and models to track the spread of the virus, predict case trends, and visualize the impact. These efforts provided the public with accessible and up-to-date information on the pandemic, and individuals could make informed decisions based on the data as a result, and health authorities could use the insights for effective responses. So, I mean, literally life-changing stuff. There's also projects for disaster response and relief. So there's been development of applications and models for basically tools that provide real-time data on disasters such as hurricanes, wildfires, and earthquakes. And again, like these are, I thought it was interesting to kind of delve into open source tools, because these are things that you and I can get access to and learn how to use and make an impact in the world with. So as a result, from having these sorts of like open source disaster response relief tools, average people can use them to stay informed during disasters and make informed decisions about evacuation and safety measures. They also help relief agencies target resources effectively and speed up response efforts. For election data analysis, during elections, communities can create tools for data analysis and visualization to track results and voting patterns. These tools enhance transparency and accountability in the electoral process. Average citizens benefit by gaining access to accurate and real-time election information. These tools help ensure the integrity of the democratic process and provide insights into voter behavior. So, Wikipedia, this one I actually didn't know about, but it makes a lot of sense. Wikipedia uses what they call their Objective Revision Evaluation Service, which is used to automatically assess the quality and trustworthiness of edits made by contributors. It ultimately ensures the reliability of the content available to the average person. So the way that it works is that it leverages machine learning algorithms to evaluate edits and assign quality scores, helping maintain the accuracy of Wikipedia articles, which I can only, I don't know, I find that pretty fascinating, because you kind of wonder, like, how do you even begin to design a system to rank that sort of thing? Like, what sort of metrics would you use? Because obviously you want to gauge on accuracy of information as well as the value that it brings to the overall entry and the overall heightened meaning. I mean, I guess things like ChatGPT are not too far removed from that, because they can bring meaningful insights. That's kind of what they're designed to do. So maybe not too far removed, but still just pretty crazy to think about that once you kind of delve into the thought of, well, how do you make the system evaluate between meaningful versus non-meaningful entries? Like, what sort of metrics does it use? Just pretty crazy. So there's OpenStreetMap, which is a collaborative mapping project that has revolutionized digital maps and GPS navigation. You heard it here, folks. Many mobile apps and services use OpenStreetMap data, making it a widely recognized tool for the average person's travel and location needs. So it allows users to ultimately contribute and edit map data, which is freely available for applications like Google Maps and various navigation apps. There is Epidemico's Health Map, which aggregates and monitors global disease outbreak. It has been instrumental in providing the public with real-time information on disease outbreaks, including COVID, helping individuals stay informed about health risks. It uses natural language processing and data aggregation to detect and report disease outbreaks by monitoring news reports, official health alerts, and social media. And then our last example here, Kaldi for speech recognition. So Kaldi is a toolkit for speech recognition, and its applications range from voice assistants like Siri and Google Assistant to automated call center services that the average person interacts with daily. It's ultimately used to train and develop speech recognition models, which enable natural language processing and voice-controlled interactions. Yeah, isn't it just crazy to see? I don't know, because you think about something like Wikipedia, you think about something like Uber or Airbnb, even one of the examples we touched on at the beginning of this, and it just works, right? You just get on your phone, boop, 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 things just work. When you really think about it, really diving deep into like what exactly it has to accomplish and what sort of problems have to be addressed and how they have to be addressed to be able to be both at scale, but also individually unique for each individual user's particular challenge or use case. It's just crazy to think about just how dynamic it is. These sorts of things are. It blows my mind. But anyways, with that, we can talk a bit on future trends. Getting towards the end of the presentation here, but I think I just have future trends, and yeah, kind of wraps things up nicely. So overall, field of data science is dynamic and ever evolving, with several emerging trends and advancements that shape its future. These trends ultimately influence the development of tools and libraries, foster collaboration, and expand the accessibility and capabilities of data science. So some of these trends, a lot of which we actually talked about tonight in terms of people interacting in the discussion, are AI and machine learning. So continued advancements in AI and machine learning, including deep learning techniques, reinforcement learning, and natural language processing, are definitely expected. I know OpenAI just released the, like ChatGPT 4? I was playing around with that a little bit. It's pretty, I mean, ChatGPT 3 was pretty crazy. 3.5 was pretty crazy, but 4 is another level. We use it in some of the organizations I volunteer for. You can even generate images now, which is a nice plus. I mean, that's been a thing with AI for a while, but nice to have it in ChatGPT as well. There's automated machine learning. So the development of automated machine learning tools is quite the trend, automating various stages of the machine learning process, from data pre-processing to model selection and deployment. So there's certain tools that will they'll ultimately just enable data scientists' productivity and accessibility to machine learning. At least some of these like open source auto machine learning tools. Another trend is interpretable and explainable AI. There is a focus on making AI and machine learning models more interpretable and transparent, allowing users to understand how models make predictions. There's responsible AI and ethics. So the trend is a growing emphasis on ethical AI and responsible data science practices, including fairness, transparency, and privacy. Big data and real-time analysis. The demand for handling and analyzing vast volumes of data in real time will continue to rise. Edge and IoT analytics, the growth of data analysis and machine learning at the edge and in the Internet of Things devices. Quantum computing. Actually, a good friend of mine is looking to get into quantum computing, wants to study, get his doctorate, and focus on that. The potential impact of quantum computing on data science, including solving complex optimization problems and accelerating certain machine learning tasks, is also a trend. There's even going to be, I don't know, just interesting. I don't know. Quantum is kind of a fun word. Whenever I hear quantum in anything, it just makes it sound a million times more, I don't know, just interesting at the end of the day. Data privacy and security advancements, ongoing developments, data privacy and security technologies and regulations. I feel like security is ultimately a game of cat and mouse. I don't think it's ever going to go away. So there'll always be trends there. Next is explainable natural language processing. Enhancing natural language processing models to produce more interpretable and explainable results. And domain-specific data science. So what we were talking a bit about before. Specialized data science applications in various industries, such as healthcare, finance, and sustainability. Like, everything needs data science, right? Everything needs to make meaning out of multiple events or multiple numbers or multiple statistics. That's kind of what we do as people. That's kind of the spirit of human ingenuity at the end of the day. We're able to make meaning out of the world, out of reality. So, I don't know. That's what fascinates me about this sort of thing. That's what fascinates me about statistics as a whole. And that's what the human enterprise will continue to do, and that's what we'll continue to do in all derived from it, including statistics, including data science, including everything of that sort. Quantum mechanics is so advanced and complex, but really overwhelming. Yes. Well, maybe I would say it's so advanced and complex and really overwhelming. Instead of but, I think all those things go hand in hand. I had a really big interest in I never pursued physics or anything in terms of education, but I had a really big interest in quantum mechanics when I was younger. I'd read all these sorts of pop science books on that, on subjects like the theory of everything, quantum gravity, trying to find a solution for it, so on and so forth. I don't know. Interesting world, that's for sure. But with that, the future of data science is characterized by advancements in technology, ethical considerations, and the increasing demand for real-time and responsible data analytics. It'll ultimately play a pivotal role in just bringing these things to the next step. So, kind of near the end of the hour here. Wanted to bring this up, bring it open to Q&A, discussion, anything of that sort. If you guys have any questions or comments, insights, scathing, bitter remarks, anything of the sort, let them open, let them be heard. Let them be heard, rather. It's been a long day at school. I think I've been here since, been here far too long, that's for sure. Melting my mind at the moment. But with that, so I'll leave this open for any questions. In the meantime, I want to explore that roadmap that I was talking about. Roadmap for AI and data scientists. So let me share my screen in that domain. Share entire screen. Share this here. Oh, not my entire screen. I want my browser. Here we go. Here we go. Okay, so yes, just for anyone looking to learn anything in tech, this roadmap.sh is a pretty cool site. Again, you have these roadmaps built by pretty competent teams. Like we had this data scientist. This roadmap was built by the AI and data science team at Careem, which is an Uber company. So if they're good enough for Uber, probably good enough to listen to in terms of how to get from A to Z. So here we have mathematics, linear algebra, differential calculus, blah, lots of heavy math. Definitely important. A/B testing. Yeah, I've actually heard that statisticians, well, keep in mind, again, in something like data science, it's such a broad field. There's all sorts of talents that can be utilized. Like for data science, you still need UI and UX, even if you're not doing any data science yourself necessarily. It might help to have some ancillary knowledge and some related knowledge, but I've heard that statisticians make absolutely wild data scientists because, well, I think for all the data insights that you possibly want, it goes into the field of statistics pretty naturally. But I've heard of things like at hackathons, they'll have some people will do data science projects. Some of them will be computer science people. Some of them will be like not even data science students. Some of them are just statisticians, and they can implement things like crazy, like they're demons at it. I don't know. I just love that so much. So let's see, statistics, hypothesis testing, probability and sampling, A/B, proving test sensitivity. DoorDash, Kupak. Curious about this. I have a lot of friends who work at DoorDash. Not doing tech, they just just extra money through college, DoorDash. Color control and use predictions as covariates that we successfully deployed. Okay, interesting. a little bit above my head at the moment, but here we go. Some nice visualizations. These are made for me. Let's see. So I'm kind of confused to learn data science and machine learning because I'm math. Why is that the case? Are you not as developed in math as you'd like to be? Like, do you have to learn a bit more to get up to the point where you can start to tackle some stuff like linear algebra and calculus? Or is it that you don't particularly enjoy math? Or that you might not particularly, maybe you think that you have a weakness in math? That's not like a subject that comes easily to you? I'm curious about that. Because I was at a point where calculus isn't very good. Is it not very good because it's hard to make sense for you of how calculus works and it's just a difficult subject for you? Or that you're just like rusty on it, or you haven't learned it very much yet? Because I was at a point, at least, where when I was in school, even like when I was in elementary school and everything, all the way up to now, I just never paid attention to math class. I don't know why. It just didn't really. Every other subject I could just kind of fly by in with minimal effort. Math wasn't that way. And being younger, I just wasn't. I guess it kind of annoyed me. So I didn't really care to put too much time into it. And two, in my last couple of years of high school, I didn't have to take math classes. There were classes on learning how to build computers and learning about computer hardware that you could take for math credits. So I just did those instead. But now that I've decided to go for engineering, well, two, I was going to go for computer science anyways. But now that I'm going in those more math-focused fields, let's just say that I did not do myself any favors by not focusing on math for all that time. So what I had to do was I had to teach myself math from the very beginning. I actually went all the way back to like first grade math, not because I had to necessarily, but because I wanted to make sure that I didn't miss any sort of fundamental principles or solutions or methodologies or mental tricks or the like that could have helped me. I whizzed by all of that. Obviously, it's pretty simple stuff, but I actually did learn quite a lot that I wasn't exposed to in school, or maybe that I just wasn't being attentive to and I never picked it up, like certain divisibility rules. Something as fundamental as that, like the divisibility rule of 3 or 7 or 9 or anything of that sort, helps so much with mental math if you have those down. Just makes it that much faster. Or two, even like designing certain solutions, like with in programming, you do a lot of stuff with like your modulo operator for finding remainders. Stuff like that really comes in handy just in terms of understanding the behavior of those things before I even go to implement them. In terms of divisibility and how modulo operator and all that relate to each other. So even going back to those foundations really helps. In fact, it was funny. I'm taking a Java class at the moment, and we had a certain assignment where we had to make a loop that printed a like a rhombus shape with only one loop. And there's all this sorts of information to it. But anyways, my math really helped me with that too, that other people kind of struggled with. So I went back to the basics. It allowed me to see more simple solutions, and I got the highest grade for that. I only had one loop, but anyways, we're at the end of the hour now. At this point, I'm going to bring things to a close. Thank you all for attending. I hope you have a good rest of the events and learn all the more about some good tech stuff. So thank you.